Hello, good evening and welcome to NARC Live on Wednesday the 16th of July 2025. Coming to you live from Norfolk on the east coast of England with Tammy M0TC.
Hello.
And me, David G7URP. Lovely to see you. On tonight's show, we find out about radar for weather with Steve KW7Q. We look back at some of the WRTC test stations from last weekend. And we find out what on earth this is for specifically. If you haven't already sent us an entry, we had quite a few in the end. You've got just time to do that on BATC or Facebook, and we'll read those out when we get to that part of the programme. But firstly, club news. Now, this is a time of year normally when I like to sort of be really positive and say nice things. But if you've looked ahead, so what should be happening is this Sunday we should have Radio by the Seaside at West Runton, which we've done for many years. But if you've looked at a weather application or the Met Office or anything like that, looking at weather for Sunday in that area, it's not looking too good. We've got a slide here with all the details on it, but I need to add this caveat that we may postpone it. Now, to make it really well, of course, we have a fantastic resource in our very own weather expert with Jim Bacon, G3YLA. He's looked at the weather for me today and said it is a bit, I think it's sort of 50-50 almost, but probably not safe to say definitely go ahead at the moment or the other way. So what we're going to do is we're going to leave it until Saturday lunchtime. I appreciate that's late notice, but you know, none of us would want to set up there with rain or even worse, thunder and lightning, which is a possibility. So the weather has moderated a little bit, but that's only my take on it. Obviously, Jim has got all of the maps and all of the expertise at his fingertips to be able to give us a really good forecast the day before. So we would love to see you this Sunday, the 23rd of July, for Radio by the Seaside. But please don't go until you've either checked our website or looked out for a newsletter on Saturday afternoon. It does take a few hours for the newsletter to propagate and get to everybody, but we will be making a firm decision at lunchtime on Saturday, and I'll update the website just as soon as that's happened. Okay, so hope to see you for Radio by the Seaside this Sunday. If not, we will postpone it and we'll just have to keep an eye on the weather. It seems ironic, doesn't it, Tammy, that we've had such amazing weather in this country the last few weeks, and yet we're having to maybe postpone something because the weather looks awful. I mean, I remember worrying about Barford when we had it.
Yeah.
And we'll come on to that in a minute. But, you know, and that was looking a bit shaky, but we ended up with a reasonable day. This, though, doesn't take all the organisation that Barford took. So I think we can call it fairly late. So please share that with everybody else. We would love to see lots of people there, which is why we won't do it unless it's reasonable weather. Now, I started by talking about Radio by the Seaside. That was for Sunday. But on this coming Monday, we're due to have the Trophy Fox Hunt, which leaves from Thorpe Recreation Ground at 7:30. People will normally come about from 6:30. But again,
let me guess.
If you look at those weather maps and the forecasts, it's not looking too good. And of course, not only would it be unpleasant to do something like that, but literally at the moment, at least on one of the apps I saw earlier, that they're talking about thunder and lightning, and there's no way that we're going to have either the Fox putting up their antennas or anybody else going out doing this stuff. It would be mad and irresponsible. So the same thing happens, though. It's quite volatile. Jim gave me a lovely complex-ish explanation about why, you know, it's to do with the low pressure and things, and that things could change. So we're not going to call this until Sunday lunchtime. So again, for the Trophy Fox Hunt, please have a look at the website from Sunday lunchtime. I'll make sure it's big and bold and obvious on the front page of the website. Plus we'll send a newsletter out so that everybody knows where they are. So that's the details. That's how it should be for this coming Monday, but it is a TBC, I'm afraid. It's the only sensible thing to do. It's a great fun. Don't worry. Again, if we can't run it on Monday safely with reasonable weather, then we will postpone it and we'll just do it in the future when we can. Thanks very much to Jim G3YLA for his honesty, all his great expertise and guidance on this. Very much appreciated, Jim. let's get on to some positive news. Got some good news for you, honestly. Because this, I've been banging on about the Hamfest for about a month now when we've been making it available. Today was the deadline for booking, at least when I had to call it. I'm delighted to say that Tammy's going to put a wonderful slide up now, which says it is confirmed. We have got enough people, well, virtually enough people to go. We've actually got 23 people who've booked and paid for their Hamfest coach trip. And to me, that's close enough to 25, because I'm sure that we'll pick another few people up beforehand. In fact, I know one person is just waiting on a date for an operation, and as that's the only reason they haven't committed yet. So that's why I'm saying now it will definitely go ahead. Thank you ever so much for all those of you who've committed and supported it so far. It was a bit touch and go, as you know, but we will definitely be going now. And we'll either be going with a 26-seater coach, which is still pretty big, or, of course, we can soon bump that up to a 52-seater if we need to, if more people than that. So you have got some time to book. But again, if you check, once you know that you want to go, please let me know, because there'll be a point before then, in the sort of around about a month's time, when I'll be saying that's the last orders for people who want a wristband to go in with, because it's going to take me, a week, 10 days to get the wristbands to me. So there we go. Really good news at last. And I just want to say a quick mention of Barford 2025. I think we have a picture here. I'm not sure if it was this year's or Tam.
It was.
It was last year's. I didn't take a single picture this year, I'm afraid. I was a little busy, I'm afraid. But that looks perfect there, doesn't it? The weather, you think nothing to worry about. But if you did come to Barford this year, firstly, I really want to thank you for coming, whether you were a trader or whether you came to visit. Although our numbers were down, as I said at the club meeting last week at CNS, we were down to about just over 200 people, 207 people actually through the gate, which when we normally get 260, 280, up to 300 through the gate. But we had about the same number of traders as usual, and because all those people came as well, it made it successful for them. We sold out of bacon rolls and it was a really good event until 11:15 when the heavens opened. But that was kind of predicted. So although we had a shorter time than normal, I think everybody enjoyed it from what I understand and from what I've heard from people. So thanks to all those who visited and supported us that way, and a special thanks to the 24 people, members of our club and members' families, who helped to run that event, to man it. It does take that many people. It may not look, you think, well, there's 24 people there, but it does take that many people to organise everything, run the stores, run the bring and buy, run the silent key sales, parking everybody, marshalling and everything. So thank you ever so much to everybody. Feeding people, yes, absolutely.
The most important job, feeding people.
And the fruitcake was lovely, Mrs. Taylor. Thank you very much if you're watching. So that's it for Barford. Next year, I can tell you when the date is. Well, I haven't got it quite on me, but it's the first Sunday of July every year. We do that so that everybody is sure. I can't give you the results, as it were, financial results from that. It is our only fundraising event a year. We took £384 on the raffle, I believe, Tammy, for the club raffle. Yeah, I think it was
386, something like that.
Whatever, I published it somewhere. But we haven't got our financial figures for the club yet, just because we're still waiting for a couple of bills to come in, and particularly the village hall, where we pay a variable amount for the energy and things we use. But we definitely were the right side of it. We made a surplus, which is the right side of the line. So it's very, very successful for everybody, I hope. Let's get on to some members' news now. Now, although Ben M7 FRS isn't a member, I believe, of NARC, he's certainly a member of the Lower Stofton District Pi Radio Club. This is a rather unflattering picture, but this is one he published, so this is it. Now, you may have heard, if you were on 2 meters around lunchtime on Monday, you may have heard Ben there. He's sitting in the back seat of I believe it was a Cessna. His dad was in the other seat, and also John G0JDL was actually the pilot, and it was also an amateur. And he was putting to the test, really, I suppose, the new license condition that we have, where you can be actually aviation mobile. What's the right phrase? Not airborne mobile, I think it is. Sorry.
Well, I think you can say whatever you want now behind it, can't you?
Well, yes, but you know what I mean. I think there's a term for it that allows. You couldn't do this before. Ironically, I mean, you could probably get a pair of PMR radios and do it, that way, but you couldn't do it this way legitimately and with our license, but you can now. So well done to Ben and John for driving, I nearly said. And that's their route you can see around Norfolk, and this is what Ben published. But it really created lots of excitement. He had a real pile-up. I managed to contact him when someone told me about it. We only knew about it, or I only knew about it, sorry, on Monday morning. I believe he had talked about it a little bit before. I saw it come up on Facebook and then shared it on the club's Facebook page. So it was really good fun to work him. I expect he'll be doing something else similar now in the future. Now, as I mentioned earlier on, WRTC is just a year away. In fact, to be specific, it's the 8th to the 13th of July 2026. So it's literally just under a year away. And last weekend, they had a kind of pilot, a sort of test transmissions, tests for putting up the aerials, tests for putting up the tents, generators and all those other things. And these are some of the pictures. Martin G7UGB kindly sent these pictures. He was involved with setting up these. And Andy M0NKR sent us these pictures of, I think there were 4 test stations. There's Steve M1ACB there, and Lee Volanti there. And you could see these were set up, I think, fairly near Thetford. There's an estate that they were setting these up, and lots of people offered help. Of course, next year, there won't just be 4 stations, there'll be 50 stations. So they needed to go through this to sort of see the sort of problems, I guess, that they might see then. Tammy, Kevin and I are actually involved next year at WRTC as well, because we're manning their live stream studio, which will bring the results, live results, and reports and interviews and everything from the event at Cambridgeshire next year. So it's really exciting. I remember when Mark M0DXR mentioned this to me a couple of years ago at Luton Rally, and just said would be interested in helping them with the television coverage. It seems so far away, but it was 3 years then, and we're now just under a year away. So look for further details. Of course, the club as well have supported them, as you know, because we've sponsored a tent, so we've sponsored a station ourselves, but I'm sure there'll be lots more details as we include the run-up. They're still taking donations as well, and encouraging donations. You get a lovely, this year, silver medal if you donate £100 or more. So have a look at their website if you want more details. It's wrtc2026.org. So it's wrtc2026.org. Finally, we'll end on a little bit of fun, I hope, for you. Now, I don't know about you, but there seems to be an awful lot of USBs around now. We just started off with a basic USB-A and USB-B, and then we had these small mini and micro USBs. And then they had a Canadian B. You've probably heard of a Canadian B, haven't you? And there's this USB. You're looking at me sort of, well, I think it's funny anyway.
Yeah, it's really
funny. And I think,
funny.
hopefully, our guests will find it funny as well. All right. Okay. Tammy, relieve me and everybody else out there.
Okay,
Little people.
Here's Little People this week. I saw this one, it's quite fascinating, really. It's called the Family Computer, the Nintendo Family Computer, which obviously it's worked into being the family computer, but it actually was what became the NES back in the 80s.
Which stands for Nintendo Entertainment System, wasn't it? Yeah. Okay.
It's pretty cool.
Does look good.
Bit Mario, you can't beat a bit of Mario, can you?
So I think, what have they done there? What is that?
Well, they've made it like into a lounge with seats, and then they've put
I
a
see.
TV
Right,
on,
so you're
which
in
is
the
like
whole
a cartridge.
Right, so the whole room becomes it.
Yeah. So
Oh,
it's
yeah.
taken the family computer and making it into a family computer. It was lost on you, wasn't it?
You know, I'm not a gamer, am I really? Sorry about that. You are. Anyway, miniature-calendar.com. New picture every day. Tammy picks one out for us. Sorry, it was lost on me. So what have you been doing? We haven't had much news from you, apart from those things from WRTC, really, and Ben. So please do keep in touch. We're going to meet again next Wednesday, by the way. So we've got, it's unusual, we normally meet alternate Wednesdays, but next Wednesday we're meeting online, and then I think we have 2 Wednesdays where we meet at the school, concurrent Wednesdays, just because availability of speakers for NARC Live. So do keep in touch. Send us your details to radio@dcpmicro.com. Love to see a picture of you on holiday or something you've been doing in the shack or anything like that that would interest other members. Just send us a picture, a few words, and we'll include them with next week's NARC Live. So now back to that competition. 2 weeks ago today, we asked you, what on earth is this for? In other words, because I mean, you look at that, a quick look, I'd say that was a pair of pliers, but it's not. It's something very, very specific. And I'm delighted to say that quite a few people got it.
You're giving the game away now?
What?
Well, you're giving the game away now.
Well, what do you mean I'm giving the
So
game?
you're saying that some of the answers are right.
Well, maybe they are, maybe they're not. But we haven't had anybody on BATC who have got an answer, and nobody either on Facebook. So let's read out the answers that we did have. First off the block was Jason 2E0JRV, said it's a pair of crimping pliers as used by OpenReach engineers to attach two wires together in either a cable joint or inside a green cabinet. The crimp 8As are gel-filled two-way crimps, and he said it also works with three-way crimps. Tammy?
Bruce G4KZT, I'm guessing this is a connector crimping tool.
Colin M0GMK says this week's object is crimping pliers used for crimping water-resistant gel crimps, frequently used for splicing telephone cables.
Martin G6WNN, I think the current what on earth is a pair of crimping pliers for jelly crimps used, for example, in telecommunication networks.
Mike G8EY says this looks like a jelly crimping tool on a Scotch lock for a Scotch lock 2 or 3 wire IDC connector by telecom engineers or something for squashing gummy bears. What? Yep, that's what he says.
Don't think of what would be a gummy bear stuck in that. Bob G6PWS says the item looks like a BT or whoever's cable connector crimper used the little jelly-filled waterproof connectors.
Well, either
I kind of get that now. Then,
do you?
When you say jelly, I didn't get what you meant by jelly.
Oh yeah.
Oh, you mean like
gummy
literally
bears.
waterproof type
Yes.
thing?
Yeah.
Oh, okay.
Well, either they're all wrong,
Yeah, maybe they are.
or maybe they're not. What are they, Tammy? What is it?
It is a jelly crimping tool for 8A and 8B crimps.
Amazing how much information. I think some people might have looked that up somewhere. You never know. Anyway, thank you. Well done to everybody there who got that right. I didn't think that was that easy. I think, well, if I hadn't have thought that it would be so easy, I think I might have said it's just a pair of pliers. So, anyway, really good. Thanks very much for entering that. I'll be honest, we're a little bit pausing here because our guest in America, who I can see on a little monitor in the corner of my eye here, is not moving. He's very stationary at the moment. It's a fixed image. So I hope, Steve, if you can hear me, because we're going to come to you very shortly now, if you've got any problems that end, maybe you can have a look, because all I can see at the moment is a frozen image from you and both your slide and your picture. Anyway, let's have a look at the next competition's picture, and we asked you, what on earth is this? By the way, Steve, thank you. We can see you now. It was frozen. Here we are. What is that for? I have no idea.
I do, because I saw the answer.
Oh, well, okay. I would have no idea. Do you know what that is? Don't use one of these googly online cheating tools. Do you know what that is? Let us know.
You've only got a week this time.
You've got just under a week, yep. 3 o'clock next Wednesday afternoon. Let us know if you know what that is or what it's for. Fascinating, I think. Can't wait to actually see what they, Anyway, mustn't say any more.
Yeah, this is a shout out to the person who sent it to us. You know who you are. Can we have a video demonstrating it, please?
Yes, good idea. radio@dcpmicro.com. That's the address to get to us. And we will need your entries by 3 o'clock next Wednesday afternoon. And then we'll be revealing all next Wednesday on NARC Live. So before we meet tonight's guest, let's just have a close look at what's happening this week at NARC. On Sunday at 7 p.m, the GB2RS News on GB3MB. On Monday night, we hope, of course Sunday, we hope, is going to be Radio by the Seaside, but it's to be confirmed on Saturday lunchtime. Check the website. Monday night, of course, we also have our trophy fox hunt, a very important one, which could gain the winners the trophy. But again, check on Sunday lunchtime, the day before, to check that it's going ahead. And then next Wednesday, July the 23rd, we've got NARC Live with Kevin N4XL, who's going to talk about the reverse beacon network and COS, which I think is carrier operator squelch, and how they could really help you with contests and competitions. So that's happening next Wednesday. And of course, as I said, please do keep sending us your stories, your pictures and everything for NARC Live. If you can get them to us by about 3 o'clock on the Wednesday, we'll try and include them in that night's programme. And of course, we do have this card, which we send nearly one a week on average, which we're happy to send to anybody who would be cheered by a card from us. This is the email address to send them to, bottom of your screen now, radio@dcpmicro.com. Now, we've been talking about the weather so far and how it might put off a couple of our events. And one of the reasons that we know about this is because we have good forecasting. Well, tonight we're going to find out more about how radar actually plays a fantastic part in that, with an expert who's coming to us live from his home in Colorado, Steve KW7Q. Hello, Steve.
Hello, David and Tammy. I'm glad to be here. My camera is moving now. You okay?
Yeah, it's all right. Yeah, it was stationary again there, but we can hear you, so that's good. But it was okay. It is moving now, so we can see you. Yeah, but so it's really good to see you. And I know we're in for an interesting evening because, of course, radar, apart from the fact that weather affects all of us in many different ways, radar is a fantastic technology which definitely uses a lot of radio techniques. So I think you're going to share with us about the basics of radar, how they work with weather, and we're going to leave you to that. If you have any questions at home, though, or comments for Steve, then you can ask them at any time during his presentation, and we'll read them to Steve right at the end. But now, over to you, Steve.
Very good. Well, hello, everyone. It's about 1 p.m. here in Fort Collins, Colorado. I'm sitting in my ham shack. It used to be my office, but it's a ham shack now that I'm retired. I was really fascinated by your meeting there, and it sounds like the weather this weekend is really great. For a meteorologist who's been around the world and studying storms, we go to where there is weather, and I've done a lot of research on lightning as well. I'm not going to talk about that today, but that's another very fascinating subject, maybe for something in the future. So, if you read my little bio, I got interested in meteorology basically when I was going to undergraduate at the University of Missouri here back near St. Louis in physics. And I had been a ham radio operator since I was 14 years old. So I had an interest in electricity, electromagnetics, and wave propagation. And I felt that going into advanced studies in the field of atmospheric science and studying in particular radar would be a great way to utilize my interest in electronics and through ham radio in my career as a radar meteorologist. And just I also want to mention, it seems like my video is trying to freeze up here, so I have to restart it. I want to mention too that my educational heritage has a strong link to the UK. My PhD advisor at the University of Washington, the late Professor Peter V. Hobbs, very well-known cloud physicist and aerosol scientist, did very important research. He was my advisor for my PhD. He obtained his PhD from Imperial College, and his advisor was Sir John Mason, who's one of the other very well-known cloud physicists in the world. So I guess my academic grandfather is Sir John Mason. So I have strong ties to the UK in terms of my advanced education. So today I'm going to talk about radar, which stands for radio detection and ranging. So we detect things using radio impulses, and we range things. And that, in a nutshell, is what radar is all about. So I'm going to talk just a little bit about radar today. And I'm going to go through some basics. I'm going to talk a little bit about the history of the development of radar, which the UK played a very, very strong lead role in, um, just in advance and at the beginning of World War II is when radar really found the niche in military applications, and then from there into weather applications. And then I'm going to talk about Doppler and a polarimetric radar, which is a very specialized radar, and some of the things that we can do with it. I'll show some examples of detecting weather with the radar, and then I'll finish up with um, some research that I've done as part of NASA and a big project with Japan to look at precipitation systems from space using a spaceborne radar. So anyway, let's see here. My hmm, that's interesting. I can't get my looks like it's okay on your end, David, but
We can
my
see your slide, although it's not
yeah,
changed,
it's
Steve.
I'm trying to advance it. There we go. I
Ah,
have my mouse. Okay, so um, let me talk about the development of radar, especially in the UK. This was right before and then at the beginning of World War II. So I did a little research on this. It was very interesting. In February of 1942, an elite team of British troops, British soldiers, made a raid, a very daring raid on a coastal radar installation that the Germans had in northern France. And they were after this prized technology that they had found out about, the so-called paraboloid Würzburg radar. And they brought pieces of that back to the UK. And shortly thereafter, in about 1942, there were as many as 1,500 scientists working at Malvern University to develop the radar techniques and applications for military. And there were pivotal advances made in the UK at the same time at the Lincoln Lab at MIT in the US that really led to the development of radar, application of radar, and the groundbreaking technology applied to that the Allies then had that played a pivotal role in World War II. And along the way, the radars were to detect ships and aircraft, but there was this mysterious echo that was called ghost echoes at the time. No one knew what it was, but we now know, and we know it very well, that these false echoes that were the radars were seeing um, was due to weather that the radar was seeing. So this is a very interesting fact. There's some really heroes in the UK that I found in this article on the Telegraph, and especially this Alan Dower Blumen, and he made fundamental contributions to developing radar in the UK, and he developed the radar that went on the Halifax bombers in World War II, and they could fly at night and detect targets and things like this. It was interesting. He also developed stereo sound system. Fascinating. He received a patent in 1933 for stereo sound. And tragically, Blue Mine was killed in a Halifax bomber crash in 1942. But the work that he did and other scientists in the UK, along with the scientists in the US, was pivotal in bringing radar into the war front, if you like. And then soon after that, um, a host of people got together and really formulated, and the field of radar meteorology began. So the field of radar meteorology is only about 75 years old. It's relatively young science. It's similar to satellite meteorology. We all know about satellite images from space, but that scientific discipline is about 75 years old as well. So tremendous advances were made in a relatively short period of time. Another World War II application that you will find interesting is this so-called Admiral Halsey's Typhoon. Well, this was the first named storm. Back in the 40s, we weren't naming storms, typhoons, hurricanes, things like that, with formal names. But this was the first typhoon to receive a name. It was named Typhoon Cobra, and it was also nicknamed Halsey's Typhoon because this typhoon was meandering about the Western Pacific, and it intercepted the fleet, the third fleet that MacArthur was using and Halsey was leading to retake the Philippines. And the meteorologists knew very little about these storms. And as a matter of fact, the the radars on the fleet carriers and that were in the third fleet detected this image you can see over here. I hope you can all see that. And they had no idea it was the typhoon. And now we know that there's a well-defined eye and the so-called spiral band around it and outer bands. We know all about these things now. We've been studying hurricanes for years. We have aircraft with Doppler radars on them that make penetrations in these storms and map the winds and provide updated information to the forecasting centers. But this was just 1944, and they had no idea what this looked like on their fleet carrier radars. They had no idea it was a typhoon, and it was a very tragic situation. About 7 or 8 ships were sunk, where sailors lost their lives in this horrific storm. So the next slide here, we're having a little bit of difficulty here and there. This was the first detection of a tornado. Now, tornadoes are fairly rare in the UK, but they're very common here in the US. This is 1953. You can see the picture here, a photographic black and white picture of the tornado, and this is what it crudely looked like on an early radar. This phosphorescent display was used, and this little appendage here is a so-called hook echo that is associated with a classic tornado of this sort. So now let me move on to radar a little bit more. This is a picture of the highest resolution weather radar in the world. It's at the Chilbolton Laboratory in the UK. It's called the Chilbolton S-band radar. And this has a very amazing antenna on it. For radar, we use a parabolic dish reflector, and that reflector is illuminated by a feed horn that sits here. We use waveguide to transmit the high power and receive the weak signal back to the radar. But the feed horn illuminates this dish, and that dish then focuses the energy into a very narrow beam, which goes out in the atmosphere. And this whole dish turns in azimuth and tilts in elevation to probe storms. This is an amazing facility. I just wanted to point it out. Every time I pause, I have to restart it. I'm not sure what's going on. But this is an image down here in the lower right from the Chilbolton radar. This just shows a rain shower, probably very similar to the rain showers you're going to have this weekend. This one is pretty shallow, only up to 4 kilometers. It would not be making lightning. It has to be much deeper and stronger and involve ice to electrify to the point of making lightning. But the radar is seeing these little echoes here. These are developing cumulus clouds that you would just detect. They're not raining yet. And these are thermals down low that may become clouds later on and eventually produce rain. This is an amazing facility, the Chilbolton radar. So let me talk a little bit about the bands that we use in radar. So we're all hams. We know about frequencies. This is sort of a picture of the electromagnetic spectrum here. And our ham bands at HF wavelengths are down in this area, wavelengths of 10 to 80 meters, 160 meters or so. But the radars use microwaves, and you have a microwave transmitter in your microwave in your house. It usually operates at C-band. I better restart again. It usually operates at C-band. So we use microwave energy for radar, okay? And we have various bands that we use in radar meteorology. The most common bands are S-band, like the National Weather Service network of NEXRAD radars uses S-band frequency. That's 3 gigahertz. well above the ham bands with a wavelength of about 10 centimeters. So the distance between the electromagnetic wave peaks and valleys as the wave propagates is 10 centimeters. That's similar to, at 40 meters, that sinusoid electromagnetic wave would have a wavelength spacing or a distance spacing between peaks of 40 meters. Okay, so just give you a little relative feel for that. Now, in the UK and in Europe, um, we use C-band radars mostly, and I'm going to restart again here. Sorry for this. I'm not sure what's going on, so have some. Please bear with me as I restart my video. I hate for it to be frozen for you. Um, in the UK, there's a very dense network of radars, and including into Europe, and they're C-band radars. So they're 5 centimeter wavelengths or 5 gigahertz frequency. Then we have a host of other radar bands that are at higher frequency, shorter wavelength, and these are primarily used on airborne platforms and on spaceborne platforms. So there's a very interesting trade-off here, if you like. Short wavelength radars like these KU and KA, they can use very small antennas to produce high resolution scanning. And that's very important for getting detailed resolution in clouds, but they're attenuated in heavy precipitation. So at long wavelengths like S-band, the reason we use S-band is that it suffers very little attenuation, but we need a big antenna similar to the chill bolt, not quite as big as it, to provide high resolution. So all of our ground-based radars are usually S-band and C-band, and the spaceborne radars are these short wavelength radars or high frequency radars by virtue of the fact that we can't fly a big antenna in space. The antenna has to be physically smaller. Okay, so on to the next slide here. So what is a simple radar system? Radar system can be very complex, but I'm going to just show you a very simple block diagram. But a radar has a magnetron or klystron, and in some cases, a solid state high power amplifier, which is capable of producing tens of kilowatts to perhaps in excess of a megawatt. 1 million watts of peak microwave energy is transmitted by these radars. Then the receiver is very, very sensitive. It can detect very, very weak signals. As a matter of fact, a single bug at 50 miles from a radar can be detected, like a grasshopper or a bumblebee. The radars are sensitive enough to detect insects in the air. And we use tracking of insects to map the winds with a Doppler radar in clear air. When there's no clouds, we can look at insects, and the insects are moving with the wind, and we can get an idea of what the wind velocity and direction is, or the speed and direction, by just looking at the drift of the bugs and the Doppler shift off the bugs. I'll talk about Doppler shift in a minute. But this is a very simple radar system. They're very sensitive. They can detect very, very weak signals, amplify that signal, and we do all sorts of signal processing on that and produce some very nice images of data. The radar sends out a very rapid series of pulses. Each pulse is a microsecond long. That is 1/1,000,000th of a second long. And we may send 1,000 of these pulses every second. So between each pulse, there's a millisecond delay. And in that millisecond, we're listening for that energy to go out and then come back. And since it's propagating at the speed of light, okay, we know then of the signal going out and coming back, we know how far it's traveled since it travels at the speed of light. All electromagnetic energy travels at the speed of light, including the signal, of course, from your ham radio. Okay, so we can then figure out the range to the targets. So the basic measurements that a radar makes are two fundamental measurements. It's return power. We send out a burst of energy and we get some power coming back from the clouds and storms. Okay, so that's called reflectivity or return power. The other fundamental measurement is the Doppler velocity. So those are the two basic measurements that all radars make. Some more sophisticated radars that we've developed, other people have developed, that we use in research are much more sophisticated, and they return many more variables than just reflectivity and velocity. I'll touch on that in a minute. So I want to leave this slide with this bottom right image of raindrops. This has a very important application that I'm going to talk about in a moment. Raindrops are not round. They're not teardrop shaped. Okay, a small raindrop is spherical. About 1 millimeter in diameter or smaller is round. But as raindrops get bigger, 2, 3, 4, 5 millimeter, which is very common in heavy rain, they're shaped like flattened pancakes. Okay, they're bigger in the horizontal than they are in the vertical. And we're going to be able to measure that with a so-called polarimetric radar. And it has very powerful applications in radar meteorology for identifying hail versus rain and improving the estimation of rain rate, which is one of the fundamental uses of radars around the world, is to estimate how hard a cloud is raining and to put out like flash flood warnings and things of that nature. So keep that in mind, the shape of raindrops, as we go on to the next couple slides. So this slide may seem a little daunting, but it's actually pretty simple. Many people think that a radar pulses out the energy and it reflects off things in the atmosphere. Well, that's true if it's detecting a lightning flash, for example, which is what we call an overdense plasma. It's all these electrons, and the wave bounces off it just like light would bounce off a mirror. Okay, that's reflection. But in the field of radar meteorology, we don't use the term reflect energy off of clouds. We call it scatter or backscatter. Okay, so here's how that works. Water molecules are what we call polar molecules. They have one end is positive, one end is negative. So if that polar molecule sees an electric field going by that's oscillating at the frequency of the radar or oscillating at the frequency of ham radio, that's too slow to excite a water molecule. But the microwave frequency is very high, and the molecule starts responding to the incident electromagnetic radiation, okay? And the molecule starts doing this. It oscillates back and forth, trying to mimic the sinusoidal variability of electric field, okay? It's a pretty simple concept. So what happens, we all know that if charge changes position, like charge on your antenna oscillates, it must radiate electromagnetic energy, okay? So as that molecule swings back and forth with that oscillating field from the radar, it absorbs some of that energy from the radar and then re-emits it. And that re-emitted energy is what we detect back at the radar, okay? So that's how scattering works. The other simple principle is Doppler shift. We're all familiar with that, right? We've stood at the side of a railroad track and a train has gone by blowing its whistle. And we know that the frequency of the whistle is higher when the train is approaching you, and the pitch of the whistle is lower when the train has passed you by and is moving away. It's similar to an ambulance, for example. Okay, so we exploit that technique in radar meteorology to get the Doppler winds. And here's how that works. So now we send out a known frequency and it hits a raindrop. That raindrop becomes like a transmitter and sends portion of that energy back to the radar. That transmitter is moving by virtue of the fact that the raindrop is moving. So that means that the frequency that comes back to the radar compared to what was transmitted is different because it's coming from a moving platform, in this case, a raindrop, okay? So if the raindrop is moving towards the radar, being blown by wind moving towards the radar, the frequency that's coming back to the radar is slightly greater than the frequency that was sent out, okay? Likewise, raindrop is moving away from the radar, the frequency that comes back to the radar is slightly less than the frequency that the radar transmitted. So we can measure that frequency shift between the outgoing frequency and the return frequency, and we relate that directly to the Doppler velocity. So that's how the Doppler effect can be applied in radar meteorology. Okay. So let me move on now and show you an example. This is how one might get the wind velocity from a radar. So this is a computer generated image of a Doppler wind velocity. This is very commonly seen in the UK when you have widespread precipitation. The blue colors indicate flow towards the radar. The red and oranges indicate flow towards away from the radar. This gray band, okay, so this example is a west wind. The wind is coming from the west. And when the radar looks north or south, it's looking perpendicular to the wind direction and it sees zero Doppler shift, right? So there's no velocity along that so-called gray band. So the orientation of the gray band tells us immediately what the direction of the wind is. And then the colors, if it's, now we know it's coming from the west, so we go around here to this height and we read off the velocity. So we can actually profile the wind in the atmosphere all the way through the depth of precipitation. Wherever it's precipitation, we can get this Doppler measurement. So that's just a little example about that. Okay. So a very classic example of how we use Doppler radar is detecting a tornado. So a tornado is a very rapidly rotating vortex that's produced through deep convection in a very unstable and what we call a highly sheared environment. The winds are changing direction and speed with height. So the radar can detect this classic hook. And if you ran an animation here, you would see this swirling around. So the tornado is usually on the back flank of the deep convective storm. Occasionally you'll have these in the UK, but again, they're very, very common in the US. But the interesting thing is we look at the Doppler velocity. This is a reflectivity image of the storm. Okay, so it shows you how intense the precipitation is. And down here, we can often see debris that's actually been lifted from the ground in the strong circulation. And we call that a debris ball. And we can identify debris in that by looking at other fields that the radar measures. It's very, very interesting. And then if we look at another example of a tornado, this was a devastating tornado that hit Joplin, Missouri in May of 2011. And I want to call your attention to the Doppler velocity image here. The radar is over here. So here's the tornado itself, the circulation. These winds are moving away. These blue colors are moving towards. So that gives you the sense of strong rotation right in this core area. And that's the actual tornado itself. So if the tornado is close enough to the radar, we can actually detect the tornadic circulation. So this has a tremendous application for issuing, severe weather warnings. So let me talk about some radars that we've used in various places around the world. And we've done a lot of work in the Amazon to look at deep convection there, in the Indian Ocean region, the West Pacific, Northern Australia, the mid-latitudes. We've done a lot of field work where we bring radars and other instruments and instrument aircraft, and we study these storms. And one of the things we're trying to do with the research is to figure out the connection between deep convection and how the entire atmosphere works. And this is a fundamental problem in trying to better understand global warming, because it turns out that clouds are one of the biggest unknowns, the biggest contributors to the greenhouse effect. So clouds typically will reflect solar radiation, and they will absorb what we call infrared radiation. So this is a really big deal for climate warming, because if you have more low clouds, it reflects solar radiation to space and can cool the planet. But if you have more deep convection that makes these large ample clouds in the upper troposphere, like 30, 40,000 feet above the Earth's surface, they absorb infrared energy that's emitted from the Earth's surface and send some of it back down, acting as a greenhouse. So we really need to figure out the role of global convection in climate change. And that's why we've been all around the world studying these storms for, in my career, almost 40 years to look at this so-called deep convection. One of the radars that we built at CSU is a very sophisticated radar that goes on a ship, and we named it Seapole, and we've taken it out. This is when we just got back from a cruise in the Pacific in 2017. We returned to San Diego. We're at sea for 6 weeks on the Roger Revelle, which is global class U.S. funded research ship. This is a portable radar here that we've taken to the Amazon. We've taken it to the Indian Ocean. We've taken it to Brazil. We flew this radar in on a C-5 Air Force transport to the Amazon jungle area, and then trucked it over very rough roads to set it up and study Amazonian convection. And it turns out that the Amazon and the Western Pacific and Africa are the three what we call chimneys around the world, where we have this major convection, major storm, and that drives the global circulation around the planet, or is a very significant component of understanding the weather global wide. Here's another picture of the radar leaving Taiwan, and this is a picture of the radar in Palau. So a lot of sea-based research that has been done. And we're frozen up again here. Hang on. Okay, so another application of radar is this CSU chill radar. This is the world's most sophisticated, highest calibrated dual wavelength, what we call dual polarized radar. Just to give you an example of what it looks like. This is the antenna. It has a paraboloid reflector, and has what we call an offset feed. And this little dish here is illuminated, and then it sends power to the big dish, and out it goes into the atmosphere. And then the reverse for the signals coming back. This sits all in a big inflated radome to allow us to turn the radar in strong winds, and also to protect the sensitive electronics on the radar antenna from hail, which would damage it. One of the capabilities of the chill radar and other radars around the world is this dual polarization capability. So I just want to mention it very briefly here in a very simple way. But hams know that about polarization. Okay, so the polarization state is defined by the direction or the orientation of the electromagnetic field, the electric field. So horizontal polarization is when the electric field sent off in the transmitter, be a radar, be your ham transmitter, is located parallel to the Earth. Okay, and then vertical polarization is when the electric field is perpendicular to the Earth's surface. So these, like a vertical antenna would be. So these polarized radars transmit simultaneously both horizontal and vertical polarization at the same time, and they receive horizontal and vertical polarization at the same time. So now we want to come back to that example of the shape of a raindrop that we talked about a few moments ago. So here's how we apply the dual polarization technology. This is a radar image of a very strong storm years ago in Colorado that we studied with the chill radar. Here's pictures of hailstones over here. Hailstones are typically round. They can be a little irregular in shape, but as they fall, they tumble, and they appear to the radar as being round. So here's the key, how we detect and discriminate rain from hail. Okay, this is very important hydrometeorological application, severe warning application, etc. So we send out horizontal and vertical polarization. So when we hit a round particle, the power coming back between horizontal and vertical is the same. And the ratio of that is then 1, right? If the power is the same. Let me fix my screen here again. My image is frozen. So the horizontal and vertical power is the same when we interrogate a round particle. But let's think about these flattened raindrops. Okay, they're flattened pancakes. A raindrop is bigger in the horizontal than it is in the vertical. So if we hit it with horizontal and vertical polarization, it's going to return to the radar more horizontal power than vertical power. Okay. So we take the ratio of that return power horizontal divided by vertical. We actually work in log units. So we take a log of that. So log of 1 is 0. So when we see hail, okay, it has a 0 differential reflectivity. And that is down here. If you look in this gray area here, you see we see 0 differential reflectivity. This is a hail core, and it's embedded in heavy rain, which has positive differential reflectivity because we're looking at raindrops that are bigger in the horizontal than in the vertical. Okay, so that's how we exploit this. And we can tell the public, for example, where the hail core is. We can also use this dual polarization capability to really improve rainfall estimation. And that's revolutionized rainfall estimation with the radar. In the old days, we used to relate the rain rate strictly to the return power, the horizontal power. Now we can use differential reflectivity and a host of other variables that a polometric radar uses to markedly improve the estimation of rainfall for light rainfall and heavy rainfall. And this is in use in the UK and throughout Europe and the US, these algorithms that were partly developed at Colorado State University here in the US. So how does your rainfall look like in the UK if you had a radar and you point it straight up and you have a precipitation system coming on shore? So you're all familiar with these radar images. This is what we call an extratropical cyclone. It's low pressure here. It has a cold front out here, and it's barreling towards the British Isles. Okay, this is common in the fall and in the winter. In an idealized sense, it has a warm front and a cold front that's illustrated in this schematic. And warm air flows up over this warm front. And this is a very unstable situation when the warm, moist air flows up over cooler, drier air. And if you look at a radar and you point it straight up in the UK, this is what most of your precipitation will look like. It's not deep convection, but it rains pretty well. It typically doesn't produce lightning or very little lightning compared to what we do in the US. But we have these little cells. These are what we call generating cells, and they're ice crystals. And the ice crystals are forming near the tops of the clouds, and they're falling down through this deep cloud, and they're growing into reasonably sized snowflakes. And then it's fairly warm in the UK, and snow is fairly rare, but just above the surface, maybe a kilometer or so above the surface, it's still snow. And the snow particles then undergo a process of melting to become raindrops that hit the surface. And the Doppler velocity shows this transition from slowly falling ice crystals. So ice crystals are big branch particles that have a lot of drag as they fall through the atmosphere. So they fall at maybe 1 or 2 meters per second. But when they melt, they collapse into a small sphere which has less drag, and it falls faster because the drag force is less. So a raindrop falls at about 6 meters per second. So the radar can pick up this transition from ice to rain very well because water reflects more electromagnetic energy than ice, because the molecules in water can move much easier than the molecules in ice, which are sitting in that ice lattice, and they can't jiggle around when an electromagnetic field hits them. So this transition, as a snow particle gets wet before it collapses into a raindrop, it's big, wet particle, so it reflects a lot of power back to the radar, and that produces this line called a bright band, and you can see the transition from slowly falling ice to rapidly falling rain. So this is what a typical day in the UK would look like with a extratropical cyclone moving across the British Isles. So I'm going to move on to the last topic, and that is spaceborne radar. And this is an example of the NASA GPM, Global Precipitation Measurement Radar. It carries two radars, two different frequencies, K-band frequencies, a very high frequency short wavelength. And this radar was built by the Japanese in JAXA, which is the equivalent of NASA in Japan, where our NASA is our National Aeronautics and Space Administration. So this satellite goes around the Earth and it samples up to a fairly high latitude, 66 degrees north and 66 degrees south. So just to give you an example, this would cover the entire UK, right? So the northern part of the UK is about 60 degrees north latitude. So this would cover the UK. And it's very interesting. It has these two radars which scan and they sweep back and forth underneath the orbit. It's about 350 kilometers above the Earth's surface. Goes around the Earth and it's sweeping through the clouds. It also carries a bunch of microwave sensors, and these don't transmit power, but they receive microwave energy that's emitted by the Earth's surface and clouds on Earth. So warm clouds, rain clouds, emit microwave energy at fairly low frequency, and ice clouds scatter electromagnetic energy at fairly high frequency. So this GPM platform has all these microwave sensors, and we combine it with the active radar to really understand what global precipitation looks like. And one of the fascinating things that comes out of this mission is these global precipitation maps. So I think you can see this image running now. And this is the last image I'm going to show before I wrap up. But let me call your attention to a few things here. You see precipitation in the tropics. Here's the equator, about right here. And we see lots of clusters of convection. We see occasional typhoons. There's one over there in the Western Pacific. And the most of precipitation is moving east to west in the tropics, you see? And now let's go to the mid-latitudes. Here's the UK up here, US, South America, Australia, there's Antarctica, North Pole is up here. And we see that in the mid-latitudes, the latitudes that we live in, the weather primarily moves from west to east, okay? West to east. In the northern hemisphere, it's moving west to east. In the southern hemisphere, it's moving west to east. In the tropics, it's primarily moving east to west, okay? So that's something fundamental that we understand, of course, and it ties into the global winds around the Earth. And the last slide I want to show, I'll just leave that run for a second. These are extratropical cyclones that are common in the northern hemisphere winter and southern hemisphere winter, okay? And they migrate from west to east and produce a good deal of precipitation. Lots of the rainfall on Earth forms in the tropics over the tropical warm ocean. That's why we've had our experiments out in the tropical warm oceans to go out into these regions to study this rainfall. And also over the tropical continents. You could see Africa here, and in the Amazon in particular, there's tremendous convection, as well as this so-called maritime continent region over here, Indonesia, Malaysia, northern Australia, where we've had experiments too. So it's a very beautiful map, but we can do these kind of maps from space now with the use of GPM. So finally, the last slide, I guess I'll have to stop this. Okay, my last slide does not seem to be coming up as I click here. There, good. Okay, there it is. So the last slide, I just want to leave you with this. The Earth and the atmosphere and the ocean is a very interesting coupled system that we're still learning lots about. I mean, there's so much more that we can do, especially how this all relates to global warming. The oceans store a tremendous amount of heat without changing temperature too much by virtue of the heat capacity of water compared to the atmosphere. The clouds are of fundamental importance, etc. But our Earth is really interesting. And let me explain just a few minutes why the weather systems move like they do. The Earth is heated by the intense sun in the tropics, and the Earth mostly cools at the poles. So the the heat comes in the tropics and it leaves via the poles. So there's a temperature gradient between the equator and the pole. There's hot air, warm, moist air at the equator, and cold air at the poles. And when they clash, when the warm air moves north and the cold air moves south, we get weather. Okay. So in the tropics, because we heat it intensely with the sun, the air is going to rise at the equator. And when the air rises, air must flow in at the base. We call that convergence. And it goes up into deep convection, and then it moves towards the poles and it sinks. And it sinks in the subtropical highs. So about 30 degrees north and 30 degrees south, the air is typically coming down. And where do we find the Earth's deserts? We find them under these subtropical highs where the air is sinking, because when the air sinks, it dries and we don't get any precipitation. Okay? And then as the air returns to the equator, as it sinks and moves back to the equator along the surface, it gets turned by the fact that the Earth is rotating. That's called the Coriolis force. So that develops our trade winds. The early sailors found these trade winds and they moved from east to west, blowing along the trades. The trades move northeast in the northern hemisphere and from the southeast in the southern hemisphere. They converge and it goes back up again. So you see this spinning cycle. So part of the air that comes down in subtropical highs then moves to the north and it collides with cold air coming from the poles and it rises again. And that produces that band of precipitation we see in the northern and southern hemisphere in mid latitudes when systems move from west to east. We call those latitudes the roaring, okay? Wind is moving from west to east. So it's a little complex picture, but I want to leave you with this because we study more things than just radar in the research. We study how it fits in with the big picture on Earth and how that relates to global warming. And this is a very intriguing map. So we live on a planet that is heated at the equator, it's cooled at the poles, and it rotates, and it has some water, some land, some big mountain ranges, and that combines to give us all the complex weather patterns that we see and that we study in our research. So anyway, that's all I have to say. I went 45 minutes, amazing that it timed out. I don't want to keep you any longer. Hopefully you found this interesting and there'll be some questions that I'm happy. So David and Tammy, back to you.
Thank you very much, Steve. Certainly has been interesting, and well, I know it's a well-used adage, but you learn something new every day. I mean, I didn't even know there was microwave energy coming out of the clouds and the earth and everything else. So anyway, if you've been watching this at home and you're watching it live on Wednesday, then of course we welcome your questions on BATC or Facebook, and we'll read them to Steve. I've got a question for you, if I can start off with this. This is the most pertinent question really, I suppose, for us, because although weather, of course, kind of affects our hobby, propagation is what we know of as really altering our hobby. So can radar be used to look at propagation itself?
Yeah, that's an intriguing question. I'm not sure I have a real good answer for that. The radar that we use to study, mostly study clouds precipitation, those don't really impact rate propagation. It works at much lower frequencies. Our HF propagation is insensitive to clouds and weather. But as we increase in frequency, it becomes more sensitive to the atmospheric structure. For example, at 2 meters, you can get ducting when you have a temperature inversion. The temperature increases with height. And some very powerful high frequency radars that we call profilers can actually profile the wind and temperature in the atmosphere and locate an inversion layer, and therefore kind of predict where a duct might be located. I guess I see really little application for traditional microwave radar in terms of high frequency propagation. But as you move into microwave propagation for ham radio, then of course you're basically using a radar, right? If you operate some of these UHF bands, they would be at close to radar frequencies. So I think I'll just kind of leave it at that. I think in traditional propagation, like the information we get from the sun, say the solar flux and the A index and K index, a weather radar is pretty much irrelevant in terms of trying to understand those propagation characteristics, But as you move into more VHF and get into more clear air propagation, radars that we call profilers certainly would have an application. So it's an intriguing question that I definitely will.
I'm sorry. I'm sorry. I ran that to you. My opening question to you.
No, it's
Steve,
fine.
but
No, it's very appropriate.
I just thought, yeah, from a radio amateur point of view,
So
it is something.
there are many questions I got over 40 years that I didn't have an answer to, and that's when one thing you always learn when you give a lecture or you give in a classroom or a seminar setting like this is you always learn something because now I'm going to go back and think more about this. I mean, I've learned so much from my students over the years. It's been wonderful. Yeah.
Yeah, well, thank you. Also, just a reminder for everybody at home, I haven't got any questions yet, which I can't believe, really, from others, because I've got loads of questions, but I better keep them down to a few. I mean, I was fascinated with, partly the shape of it. Maybe I missed it in school or wasn't concentrating on something, but the shape of raindrops and things like that, and the fact that you can use radar to tell, what it is, whether it's hail or whether it's rain and things, but specifically how hard it's raining. Can you just elaborate a little bit more on that? Because you said you could tell, couldn't you, with how hard it's raining just by these reflections and Doppler and stuff.
Yeah. So I'm going to cite an example of a research we did here in 1997. We had a Fort Collins flood. There was a tremendous event that occurred. 5 people lost their lives that night here in Fort Collins. It did tremendous damage. The university library was completely flooded. The basement level with all the volumes of books down there, etc. And there was a very benign looking storm that sat about 5 miles west of Fort Collins over the Spring Creek that flows through Fort Collins. And the Weather Service in those days, before dual polarimetric, we had just radar return power and related that to rainfall. And this was a storm that was more tropical-like. And tropical rainfall has a very high concentration of small drops. And the relationship that the Weather Service used to estimate rainfall from reflectivity was based on typical mid-latitude precipitation, where we have melted ice particles and we have a low concentration of big drops. Okay? So a very high concentration of small drops can rain much more heavily than a low concentration of some big drops. Okay? So when we used then the chill radar that night compared it to the Weather Service radar, the Weather Service radar estimated 5 inches of rain in a 5-hour period from the storm. The ground-based measurements gauges showed 9.8 inches fell, actually double the amount the radar estimated. And the chill radar got 10 inches using the polarimetric capability. So what we did is we looked at both reflectivity and difference reflectivity. And so when we see high reflectivity and low difference reflectivity, that means we have lots of semi-round drops in high concentration, and we up the rainfall rate that the reflectivity alone would give. Okay? So we developed a relationship that the radar meteorology community, the National Weather Service, then used when we had these rain events. And one of the things that tipped us off about this event is that it was raining very heavily, but it was not making lightning. So that tells us that it's tropical-like rainfall. It's raining from mostly a warm rain process. It doesn't involve ice, which you need to electrify the cloud. So the Weather Service then used our relationship whenever they saw high reflectivity and no real-time lightning. they switched to this tropical-like relationship, which actually increased the rain rate, and they improved their flash flood prediction enormously. So that's just one example of how you can combine these different fields that a pulvemetric radar measures to improve rainfall rate estimation. The accuracy is much higher now with the pulvemetric capability. It's really revolutionized rainfall estimation.
Yeah, it's a fantastic subject. You do remind me of a mutual friend, I think, Jim G through ILA, because it's. I mean, you wouldn't. Well, I don't think there's enough. You wouldn't have thought there was enough to this to keep talking about. You said you've been doing this, I think, 40 years, and it's extraordinary. I mean, when you consider that radar itself is quite a reasonably old invention, isn't it? The principles, and yet you're still using it now.
It's still pretty. I mean, we're still inventing new ways to process the data. We're developing new technologies, new antenna technologies. For example, the military has what's called phased array radars for years, and we're just now trying to get that into a meteorological application. A phased array radar is not a big antenna that we mechanically steer in azimuth and elevation. It takes time to move a big antenna and point it up in elevation and steer it in azimuth. But a phased array radar can control the scanning electronically. It's a whole bunch of little dipole panels on the phased array element, and they're excited in phase and out of phase to steer the beam electrically. So the panel can sit like this and not turn, but the beams can go shooting off in all directions in this phased array technology. And that's trying to be the next big push in the US and other places in the world, is to use the phased array technology so we can get very rapid scans of storms. Instead of looking at storms in a big storm in 4 minutes, we can look at it maybe in 40 seconds and improve the temporal resolution of that sample. And hopefully that would lead to better real-time forecasting to just see how the storm is changing dynamically on a very small scale. So phased array technology is really coming into advanced state now in radar meteorology. That's just one of other examples that are always pushing the field forward.
Yeah, it's fantastic. And again, learning something new every day. It was a few weeks ago, maybe a couple of months ago, on NARC Live, when we learnt, incidentally, to a talk about how Starlink works, and they're using these phased arrays, aren't they? With these, with their seemingly flat dishes, but there's lots of little active dipoles in each one. So
Correct.
It's fantastic technology.
Right.
Now, Jim G3YLA has been watching this live, and he says this: absolutely fascinating stuff, Steve, and it's just like being back in work. I'm not sure if that's a good thing or a bad thing, Jim. I'm sorry if we do that. One of my challenges in marine forecasting was predicting wave height. Are there any satellites that make the sea state measurements more reliable nowadays?
Yes. Those are called scatterometers. And I'm not an expert on scatterometry at all, but we're basically using glazing angles of radiation from the platform off the ocean surface to detect the surface state of the ocean in primarily wave heights. So there's a couple scatterometers that are currently flying that are giving some gradient on wave heights. Matter of fact, some of the cruises that we have been on, we of course know the wave height by looking at the ship data. We could grossly estimate it from a Beaufort scale, right? After Admiral Beaufort, very interesting person, and we also can measure the wave height with the ship radars pointing at low angle. And we can compare that to scatterometers. So I know NASA has a scatterometer that's in orbit, and it's using the technology to map surface heights, wave heights.
Yeah, well, that's good. Thank you very much for replying for Jim. He's actually added a PS to this and says, do you think that he could fit one of your dishes in his backyard?
In whose backyard?
His, I think.
Oh, Yeah, have him go down and talk to the people at Chillbold. You might want that 82-foot diameter dish. And it's been, wonderful meeting Jim. We're both members of FOC. We've been on a few calls together, and I've done some investing of his career. I'm really honored to know him. He's a brilliant scientist, and I love talking to him. Yeah, and we will do that again more.
Yeah, that'd be lovely. I'm sure he'll enjoy that. He's, as you can tell, we're very, very proud and pleased to have him as one of our members as well, because he, apart from all of the knowledge and experience that he imparts to us, it really helps as well when we've got a weekend coming up like this, when we really need a pinpoint weather forecast for our events. But anyway,
I think that if the weather's bad, if I was there, Jim and I would be out there on a hill watching the weather.
Yes, yeah.
I can talk to him about lightning, my lightning research then.
Yeah, another friend of mine is a storm chaser, so he does that. It's weird when all of us stay in the house and
Right.
get down. He's out there and going off there.
Yeah. Yeah.
Steve, it's been a wonderful journey. Thank you so much for tonight. Thank you especially. I noticed that you've tailored this talk very much for the UK audience, so really grateful for you doing that. More than we could expect, really, from some.
Well, the UK has played a tremendous role in global meteorology. Who is his book is on my bookcase here. He founded the UK Met Office and developed the first radio telegraph signals of weather data around the UK. Help me, someone must know his name. I'm embarrassed.
Is it Robert Fitzroy?
Fitzroy, yeah, the captain of the Beagle, and that, yeah, it's a tremendous read, the UK, Keith Browning and other leading scientists in the world are from the UK, and they blazed a trail well before me in radar meteorology. And I remember as a PhD student reading many papers that were written in the 50s and early 60s by scientists in the UK. And of course, my advisor, Peter Hobbs, was from Imperial College, and Sir John Mason, his advisor, from Imperial College. So there's a strong tie to the UK for sure. And I have many colleagues at the Met Office and the European Center for Medium Range Weather Prediction, ECMWF forecasting rather. That's just a world leading entity in terms of numerical forecasting of weather. Thank you.
Wonderful. Steve, thank you ever so much for this evening.
You're very welcome. Nice to meet you, David and Tammy, and maybe we'll do this again on another subject someday.
I look forward to it very much. Thank you very much.
You're very welcome. Bye.
Thanks very much to Steve KW7Q there for a wonderful talk all about radar and weather and the relationship between the two. There's so much, isn't there, to learn. Just a quick look before we finish the programme at this coming week at NARC. As I said, all being well, Sunday, Radio by the Seaside, weather permitting. So do check the website and your email inbox on Saturday lunchtime afternoon. On Monday night, we hope to run the Trophy Fox Hunt. That's certainly what's planned, but we're going to keep an eye on that weather, thanks to Jim giving us a pinpoint forecast. So again, look on the website then on Sunday lunchtime and afternoon for a newsletter. I will make sure I send extra newsletters and things just to make it really clear to people whether these events are happening. The next Wednesday, we're back here for NARC Live, July the 23rd, that is, with Kevin N4XL, when he'll be talking about the reverse beacon network and carrier operated squelch and their relationship, particularly for contesters. And also, please do send us your stories, your pictures. And also, I tell you, we really are after some mystery objects now. We're getting towards the end of our stock. I think it was Christmas when I first reminded people again we need a few more. It's kept us going till now in the middle of July, but we do need some more. So if you've got some wonderful gizmo or something lying around your house and you think, I bet they don't know what that is, then please do send us a picture of it and a little description and a name, and we'll be glad to use it in our competition. The other thing is, it reminds me of probably a year or so ago now, when someone sent us something that they found in their house and they didn't know what it was. Do you remember? And he literally didn't know. So if you've got something around your house that you don't know what the heck it's for, you could send a picture of that as well, and I'm sure someone will be bright enough amongst our audience to tell us that really did work well that time.
You'll have to have a rummage through your drawers.
Well, And on that note, I think we just have to say thank you again for joining us tonight. And we'll look forward to seeing you next week if we're still on the air. From Tammy M0TC
Bye-bye.
and me, David G7URP. Take care of yourselves. Look after each other. Bye-bye.